All right, we'll begin section 1.4, which is called composition of functions. There's a definition there. It says, let f and g be functions. Then the composite function, which is denoted by this guy here, the way that we read that is f composed g, is defined by f composed g of x equals f of g of x. Okay? So you're basically plugging one function into another, and then you're going to simplify that. So let's take a look at an example here. If f of x equals x squared minus 3x and g of x is 2x plus 1, f composed g of x, that's, again, by definition, f of g of x. So we're going to have to plug g into f, everywhere that we see an x. G of x is 2x plus 1. So I need to find f of 2x plus 1. So I need to replace x with 2x plus 1. There's a couple of x's that need to be replaced there. So I'm looking at 2x plus 1 squared minus 3 times 2x plus 1. 2x plus 1 squared, that's the same thing as 2x plus 1 times another 2x plus 1. So when I FOIL that out, that would be 4x squared plus 4x plus 1. And then distribute the negative 3 there, it would be minus 6x minus 3. When I combine these like terms, I have 4x squared, and then 2x minus 6x is minus 2x, and then 1 minus 3 is negative 2. So here's the answer. It would be 4x squared minus 2x minus 2. Okay, now just like any other function, there's input values and output values. So like if we want to find f composed g of 3, there's actually two ways that we can do this. We can handle that just like we did x. So f composed g of 3 means that I need to find f of g of 3, just like when it was x. Okay, g of 3 is 7. So 6 plus 1 is 7, right? So in other words, I'm asked to find f of 7. Okay, if I plug 7 into f, 7 squared is 49 minus 21, that gives me 28. So 28 would be the answer. Okay. Also, I don't need to redo the problem again if I've already found a formula for it, for f composed g of x. So like if I let x be 3, let's just go ahead and plug 3 into this guy that we've got circled. If we do that, we have 4 times 3 squared minus 2 times 3 minus 2. Okay, 3 squared is 9 times 4 is 36, minus 6 is 30, minus 2 is 28. So we still get the same answer. Okay? Now, there's a note here. F composed g of x, that's not the same thing as f times g of x. Some students get mixed up with that. Okay, if I want to find f times g of x, that is the same thing as f of x times g of x. And so if I take x squared minus 3x times 2x plus 1, I would need to FOIL that. I get 2x cubed. And then x squared minus 6x squared is minus 5x squared. Negative 3x times 1 is negative 3x at the end. Now that's not the same thing that I had right here. Okay? So those are two different results. I'm doing two different things there. Now what if we want to find g composed f of x? So whatever function is written after the open circle, that's the one that you're going to be plugging in first. So I need to find g of f of x. Okay? F of x is x squared minus 3x. So we're asked to find g of x squared minus 3x. And everywhere that we see an x in g, there's only one x showing, I need to replace that with x squared minus 3x, and then simplify it. So I got 2 times x squared minus 3x plus 1. That gives me 2x squared minus 6x plus 1. I go ahead and circle that. Okay, now something else to point out here. Notice how that f composed g of x is not the same thing as g composed f of x. You get two different results there, okay? Now, sometimes it will happen where these are the same thing, okay? When that happens, it's special because f and g are called inverses of each other. Okay, and we'll talk about inverse functions in section 1.6. Okay, but just know that you're doing two different things, and so it wouldn't be surprising to us to get two different results there. Okay, now there are many real life examples of function composition. The output values for one function are the new input values for another function. So one example that I like to give is like a car wash. Suppose that it costs $5 to get the car wash. Okay, but you've only got dollar bills, okay, and the car wash machine takes coins. So let me ask you, are you going to try to fold up the $5 bill there and shove it in the coin machine? No, not unless you want to lose your money, right? So you're going to have to go get some change. Okay, so the output values from the one function are the new input values to another function. So the when I put in a $5 bill and I get a bunch of quarters, that'd be the new input values to the car wash machine. Now I can get the car washed, right? Now there's lots of real life examples. Like I said, the example to give for function composition is conversion formulas. Like suppose I wanted to know how many miles or how many inches are in 1 mile. I don't know. Okay, but if I knew how many inches are in a foot and how many feet are in a mile, I could very easily find out how many inches are in 1 mile. That's function composition. Okay, or like in science classes, you do a lot of things with temperatures. And the common units for temperatures are degrees Fahrenheit, degrees Celsius, and then kelvins is another common temperature to give. Okay, and suppose that I had a temperature in degrees Fahrenheit and I wanted to change that to kelvins. Okay, well there's a formula that changes a temperature in degrees Fahrenheit to degrees Celsius, and then there's another formula that changes a temperature in degrees Celsius to kelvins. So I can very easily find out what temperature in degrees Fahrenheit would be in kelvins. Okay, here's another example. So like what if I had what if I want to know how many cups are in 1 gallon? I don't know. Okay, but if I knew how many cups are in a quart and how many quarts are in a gallon, I could very easily find out how many cups are in a gallon. That's function composition. Okay, so the example is conversion formulas. That's where you're using function composition. Now, suppose that we want to find the domain of f composed g. The first thing we have to know is the domain of g, right? Because g is being plugged into f. So we have to know what numbers we can plug into g first before we plug those into f composed g. Step 2 says that you're going to compute f composed g of x and simplify. Simplify as far as you can go. And then once you're in complete simplified form, you're going to then determine the values of x. Okay? The domain of f composed g will be your answers from both steps 1 and 2. Okay? So let's take a look at an example of that. Suppose that f of x is 1 divided by x plus 2 and g of x is 4 divided by x minus 1. There's a couple of things that I'd like us to do here. The first thing, let's find f composed g of x, and then we'll state the domain of f composed g. F composed g of x, by definition, means f of g of x. So you plug in g into f. Again, whatever function is written after the open circle, that's the one that you're plugging into the one that's written before the open circle. Okay, now g of x is 4 over x minus 1. So I need to find f of 4 over x minus 1. Well, everywhere there's an x in f, I need to replace that with 4 over x minus 1. There's only one x showing there. So let's go ahead and replace it. I get 1 divided by 4 over x minus 1 plus 2. Now, if I want to do anything with domain, which I do here, I'll need to simplify this. So I get 1 divided by 4 over x minus 1 plus 2. Now I'm going to get my common denominator down under of x minus 1. So with the 2, let me multiply the top and bottom by x minus 1. So I got 2 times x minus 1 divided by x minus 1. Now the denominator is the same, x minus 1. So I can keep the denominator and add the numerators. I have 4 plus 2x minus 2. Make sure that you distribute. 4 plus 2x minus 2. Well, that's 2x, and then 4 minus 2 is 2. 1 divided by 2x plus 2 over x minus 1 means that I would flip the denominator, and I'm looking at x minus 1 divided by 2x plus 2. That would be as simplified as I can get things. Okay, so I'd circle that result. Now, the domain of f composed g, I need to first find the domain of g. Here's g. So I know I can't divide by 0. I can't let x be 1, right? Because 1 minus 1 gives me 0 down under. Okay, so x can be any number, just not 1. And the domain of f composed g, I'm going to start by saying the set of all x such that x is not 1. And then in step 2, I need to compute the composite function and simplify. Okay, I've done that. Here's my answer in complete simplified form. And I'm supposed to determine the values for x. So if I set 2x plus 2 equal to 0, subtract 2 and divide by 2, x is negative 1. That's what I don't want. I don't want x to be negative 1 because I can't divide by 0. So in all, I can't let x be 1, and I can't let x be negative 1. Okay, x can be any other number, though. Let's try g composed f of x. So g composed f of x means that I'm going to plug f into g. So g of f of x is what we're finding there. F of x is 1 over x plus 2. So everywhere that I see an x in g, I need to replace that with 1 over x plus 2. There's only one x showing there in g. Okay, so I replace that. I got 4 divided by 1 over x plus 2 minus 1. And I'm going to have to simplify this. So I'm looking at 4 divided by 1 over x plus 2 minus 1. 1 is the same thing as x plus 2 over x plus 2. Right? And that's how I'd want to look at that because now I got my common denominator. So I keep the denominator and I add the numerators. I'm looking at 1 minus x minus 2. Make sure you distribute. 1 minus x minus 2. 1 minus 2 is negative 1. So we got negative x minus 1 up top there. Now 4, that's the same thing as 4 over 1. Okay, and that's how I'd want to think of this because the next thing is that because I'm dividing by a fraction, I want to flip the denominator and multiply. So I'm looking at 4 times x plus 2, that'd be 4x plus 8, divided by 1 times negative x minus 1. Okay, and go ahead and circle that result. That would be my answer in simplified form there. The domain of g composed f. So the first thing I have to know is the domain of f because f is being plugged into g. So we have to know what numbers we can plug into f before we plug them into g composed f. Well, here's f of x. Okay, it looks like x can't be negative 2, right? Because you can't divide by 0. So the domain of G composed F, I'm going to start by saying the set of all x such that x is not equal to negative 2. And then I look at my answer here, and I got to state its domain. Okay, and we've simplified. X can't be negative 1 also, right? Because negative x minus 1 equals 0 means that x is negative 1. I can't divide by 0. So in all, the domain of G composed F is the set of all x such that x is not equal to negative 2 and x is not equal to negative 1. Okay, here's another example. So if we want to find F composed F of x, that's saying plug F into itself. Okay, well, F of x is 1 over x plus 2. So everywhere that I see an x in F, there's only one x showing, I need to replace that with 1 over x plus 2. So I got 1 over x plus 2, and I need to simplify that to do anything with domain. Okay. Now 2, that's the same thing as 2 over 1. So I'm going to get my common denominator down under of x plus 2. 2, if I multiply the top and the bottom by x plus 2, then I got my common denominator of x plus 2. So then when I add the numerators here, I'm looking at 1 plus 2x plus 4. Well, that's going to be 2x plus 4 plus 1 is 5. So 1 divided by 2x plus 5 over x plus 2, if I flip the denominator, okay, that's going to give me x plus 2 over 2x plus 5. And that would be as simplified as I can get things. So go ahead and circle that answer there. And the domain of F composed F, so the first thing I have to know is the domain of F, right? And that's obvious because I'm only using F of x, right? So the domain of F is, we've already said that right here. It's the set of all x such that x is not equal to negative 2. Okay, and then the next thing, I'm going to take a look at my answer on step 2 and determine the values for x. Okay, I've simplified this. And if I set the denominator equal to 0, 2x plus 5 equals 0, I get x to be negative 5 halves. That's what I don't want, because I can't divide by 0. So all in all, x can't be negative 2, and x can't be negative 5 halves. Okay, that'd be the answer there. So now function composition will come up again. So it's very important that we look at the homework here and get good at that. Okay, so have a look at the problems that are on page 60, and in the next video we'll start in on 1.5.